Good day, everyone. My name is Imivan Aliki Subramaniam, and my ID number is 251291722. Today, I will be presenting our project title, Power Quality Enhancement in Solar Photovoltaic System using filters, active filters. And as you know, the adoption of standalone PV system for off-grid application is increasing. However, this system face significant challenges regarding power quality and specifically voltage fluctuation and instability. These issues stem from the intermittent nature of natural irradiance and the presence of nonlinear loads, which introduce harmful harmonics into the system. To address this, our project focuses on designing to an active power filters, unlike traditional passive filters that rely on the resistor and inductors. And active uses components like operation amplifier to provide precise frequency control and gain. Our specific objective to design a high-pass active filters capable maintaining a single-phase nominal AC voltage of 230 VRMS for 3000 watt PV system. This design includes a switching frequency of 10 kHz and 25% design margin to ensure the system remains robust even under a sudden load variation or a fluctuating environment condition. And then we are moved to the methodology. Component. I will now discuss the core components used in the circuit in our circuit. To build an effective active high-pass filter, we utilize several key electrical elements. For example, a resistor. These are used to provide electrical resistance, helping to lower current flow, divide voltages, and bias the active elements within the circuit. And then capacitor. These passive components store electrical charge in the electrical field in our high-pass configuration. Capacitors are essential for blocking low-frequency signals while allowing higher frequency to pass. And then voltage sources. We use this to maintain a fixed voltage for the circuit, which is critical for stable simulation and testing. And the last one is the LM741 operation amplifier. This is the brain of our active filter. It is a monolithic integrated circuit that allows us to achieve the necessary gain and precise signal processing required to surpass low frequency noise and harmonics. By combining these components into a cell and key configuration, we can accurately identify the mitigate distortion caused by the non-linear loads, ensure a clean 230 VRMS sine wave output from the consumers.
Hi, madam. My name is Surendan, son of Tinagaran. My metric number is 241361696. Okay, now I am going to explain about the flow chart. AC input link. This is the input signal coming from an external source. The signal is an alternating current AC signal that needs conditioning before use. The second one, internal input coupling capacitor. This capacitor block any DC component from the input. It allows only the AC signal to pass to the next stage and protects the circuit to ensure stable operation of the OPM. Number 3, RC network filter. The resistor network shapes the frequency response. It also filters out unwanted noise and limits the signal to desired frequency range. This stage improves signal quality before amplification. Number 4, operational amplifier. The amplifier filtered signal. It also acts as a buffer, preventing signal loss. The OPM provided high input impedance and stable amplification. Number 5, feedback network. The feedback resistor control the gain output of OPM. By adjusting this resistor, the output signal strength can be increased or decreased. The last one is output, V out. This is a final output of the circuit. The output signal is clean, amplified, and suitable for further processing or measurement.
Good day, madam. My name is Arvinda Sanakalisagan. The matric number is 241291219. So today I want to explain about the calculation part. So this is our calculation part. So V out equals to V in times with R2 over R1 plus R2. So V in equals to VRMS times with square root 2. So our VRMS value is 230 volts. So we need to find the V in. So I get the V in answer is 325.27 volts. So desired V out is 10 Vp and R2 over R1 plus R2 equals to V out over V in equals to 10 volt over 325.7 volt. So we get the 0.0307. So we want to find the R2 value now. So our R2 value is R2 over 1 mega ohm plus R2 equals to 0.0307. So the R2 value is 31.67 kilo ohm. So for the 31.67 kilo ohm, we round off, we get 32 kilo ohm. So for the capacitor, firstly we need to find the XC first. So the XC formula is 1 over 2 pi FC. So frequency our is 10 kilohertz. Assume that our X1 is 1 kilo ohm. So C equals to 1 over 2 pi bracket 10 kilohertz and 1 kilo ohm. So we get 15.92 nanofarad. So we round off and get 16 nanofarad. So our value R1 is 1 mega ohm, R2 is 30 kilo ohm, R3 is 10 kilo ohm, R4 is 10 kilo ohm, and capacitor 1 and capacitor 2 is the same value, 16 nanofarad. So the power supply V in is plus 15 volt and minus 50 volt, madam. And the amplitude is 1. Okay, so I show now the circuit, madam. So this is our circuit. So firstly, we take the LM740, the OPM, and the 1 mega ohm, and the C1 is 16 nanofarad, and C2 is 16 nanofarad, and the R2 is 32 kilo ohm. As a calculation, we get 31.67 something. So we take the 32 kilo ohm, and R3 and R4 is 10 kilo ohm, and the voltage is 15 volt and plus minus 15 volt, madam. So let's simulate now. So now simulation. So our V in is, this is our V in. So the dB like 47.234 dB, and the kilohertz is close to 28 kilohertz and 0.0 mm. So next is our V out. So our V out is starting from the high pass filter. So high pass filter we get the 51.9 dB, and it goes to the like 32 darja, madam. And the low pass filter is starting from the 53.2 dB and going to down like -3. So this is our high pass filter and the low pass filter for the V out, and the straight line is the V in, madam. It's going for the value is 47.234 dB. Okay, that's all from my part, madam.
Okay, my name is Anbarasan, son of Kalisharwat. My meter number is 241361659. Now I will explain the simulation result. So This is the VIN. So the simulation setup and output of active high pass filter used in solar photovoltaic system. This simulation was carried out to analyze how effectively the filter remove low frequency noise from the signal. From the simulation waveform, we can observe that before filtering, the signal contains unwanted low frequency components which can affect the accuracy of sensitive equipment in PV system. After applying the active pass filter, the output waveform become much cleaner. This show that the filter successfully attenuate low frequency noise while allowing the desired higher frequency signal to pass through. The second one is V out. So for V out is the result clearly indicate the high pass high, high pass active filter reduce the impact of the low frequency noise in the photovoltaic system. This improvement signal quality and increase the accuracy of monitoring and control within the PV system. The smoother output waveform demonstrate improved power quality, which is important for protecting sensitive electronic component and ensuring stable system operation. Overall, the simulation result validate the effectiveness of the proposed active filter design in increasing power quality in solar PV system.
Now, madam, I'm going to talk about the conclusion. In this experiment, the integration of high-pass active filter with the solar photovoltaic PV system was investigated to access the efficiencies in improving power quality and mitigating low-frequency disturbance. The use of the high-pass filter successfully demonstrated its ability to attenuate unwanted low-frequency harmonic and noise generated by the solar PV inverter, particularly those resulting from switching operation and grid interaction. By allowing only higher frequency component to pass through while filter out lower frequency disturbance, the filter improve the overall stability and efficiency of the system. The result indicate that the high pass active filter help reduce the impact of low frequency noise on sensitive equipment and extends the accuracy of monitoring signals with the PV system. Furthermore, it contributes to the overall grid stability by ensuring cleaner power delivery to the network. Although the filter's performance was promising, further research is required to optimize its design and integration, particularly for a large-scale solar PV installation where dynamic fluctuation and complex power quality issues are more prevalent. Overall, the experiment confirmed that high-pass active filter are a viable solution for exchanging power quality in solar PV system, promoting their effective integration into electrical grids. That's all, madam. Thank you.